So it is my honor to introduce Emma. She is a fourth year PhD candidate in engineering sciences and applied math. She has 2 BS degrees, 2 MS degrees, in addition to the degree that she is currently working on. So, wow. She is a NSF Graduate Research Fellow. She has also won lots of other awards, and honestly, I don't have time to list them all. Another thing about Emma is that she is passionate about science diplomacy in the Middle East, and she's actually been very involved in the Malta conferences, which bring scientists together from 15 different Middle Eastern countries. Another kind of fun fact about Emma is she is not just confined to the academic realm. She is also a classically trained violinist and plays piano as well. She also does judo, and she has been learning Arabic on the side. And she has 2 cute cats, Mary and Pippin. And Pippin has a double jointed tail, apparently. So anyway, we are really pleased to have you here, Emma, and feel free to take it away.
Thank you so much for that great introduction. Given that my headphones aren't working, you might actually hear Mary and Pippin, who are in the room over there, meowing angrily at not being let out right now. But I'm really happy to be here today, albeit virtually, and talk to you about catalyzing collaborations and the dynamics of team formation at in-person and, aptly for today, virtual conferences. So this is work that we've done at Northwestern University with our partners in Arizona at the Research Corporation for Science Advancement. Now, the first question is, why do we care about this question? Why study scientific conferences in the first place? And this isn't something that I have up on the side, but Nicholas, since you mentioned that I've been interested in science diplomacy for a long time and working with the Malta conferences, that's actually was a big motivation for me in starting to study this question. So the Malta conferences are a nonprofit that bring together scientists from all 15 Middle East countries to spend 5 days together. And it's a very complicated conference to organize for obvious reasons, and also a very expensive one. So when I was working with the Malta conferences, I got interested in game theory and really interested in this idea that we can use math to understand complex social systems. And I started to wonder, can we use math to help endeavors like the Malta conferences be more effective? And so that's really what has driven this work. But when we started it, I also learned that conferences beyond the Malta conferences are actually a huge industry. So conferences in the US alone cost billions of dollars per year. And a lot of people today, with the shift to a virtual setting, have had some discussions about the cost of conferences beyond just the monetary costs, but also the environmental costs, the millions of tons of carbon dioxide, for example, that you can see that are generated by these scientific meetings. And when you make the decision to go to a conference, or the decision which I'm grateful for to show up today to this seminar, you also have an opportunity cost of coming to this meeting versus perhaps working on your research. Now, there are a couple different purposes of conferences. Some of them might be, in the case of science diplomacy, a little different than some other conferences like large meetings, the APS or the JMM, for example, where one of the main purposes is to go, network, and learn some new exciting research that's going on. But another of the purpose of conferences is actually to form new scientific collaborations. And conferences are a particularly good place for this to happen because you meet people that you might otherwise never have met. So we feel, especially in light of COVID-19, that we needed data and analysis to try to address this question of how effective really are conferences at forming collaborations, and then beyond that, how do these collaborations affect the pursuit of science? So to do this, we set out to develop a mathematical model that would predict how likely people who co-attend a conference are to form new collaborations. And more specifically, the model would determine the probability that 2 participants at a conference form a collaboration given their interaction throughout the duration of the conference. And I'll go a little bit more in detail about what each of these things mean in a bit. And when we set out to model this, we thought of the saying by the physicist Zajdela in 1996, do humans behave like atoms? And we based our model on this idea that scientists at a conference are like molecules in a solution. And the formation of the reaction, the chemical reaction, is the formation of the scientific collaboration. So we make some very simple assumptions considering this pair of participants at a conference. Assume that the collaboration probability, which we denote P of T, is going to rise as you spend increasing time interacting. We also assume that more intense interaction, you can think of it as the more concentrated the solution, like this figure on the right, makes the probability rise faster. And finally, when the interaction ceases, the probability of collaborating decays. So from these assumptions, we wanted to write the simplest possible model that could follow this. And we're going to do this as a linear model for this reason. And although we know that people aren't necessarily following linear growth laws, we use this principle of parsimony, which is also known as Occam's razor. I like this little cartoon on the right. Actually, Occam, the simplest explanation is that you need an electric razor. So we start with the simplest possible model, which is remotely plausible. Again, we make some assumptions here. Assume that the probability of collaboration P is going to be bounded between 0 and 1. Now, when there's interaction between the participants, and I will explain a little bit more what I mean by interaction in a few slides. When there's interaction I, the probability dP dt is proportional to the strengthening rate, which we call S, times I over the maximum possible interaction times 1 minus P. And that when interaction ceases, you get a decay process with rate W, so dP dt is proportional to minus WP, where W is some positive constant. So we combine these two equations to get an equation dP dt is equal to the strengthening term when the participants are interacting, minus this weakening term when the participants cease their interaction. And we formulate it this way so that we can keep the desired fixed point at P star is equal to 0 when the interaction is 0. So when there's no interaction, the probability of a collaboration forming is 0. So dP dt is equal to minus WP in this case. And we also write it so that we have a fixed point at P star is equal to 1. So the probability is maximal when I is equal to I max, so when the interaction between the participants is maximal. Now we introduced some generalizations to this model. And the first one is this parameter P min. And that corresponds to the fact that we're not necessarily capturing all the effects that might lead two participants to collaborate. You can think, for example, of network effects, because we're having the simplifying assumption that we're just considering a pair of participants, but maybe I met Nicholas and Nicholas met Juan, but I don't know Juan. And so you brought us together and we formed a collaboration without ever actually having interacted. Or you can also think about in a conference, all of those informal interactions that might not be captured, like coffee breaks or meals, for example. So we introduced this parameter P min into our previous equation, again, changing it so that the fixed point when the interaction is 0 becomes this P min, this minimal probability of collaborating. And you can see here, it's a fixed point when P is equal to P min. We also introduced this other parameter P max, and this corresponds to the fact that even if you've interacted maximally with someone, you're never going to create a collaboration with 100% certainty with that person. So we have the model so that when the interaction is maximal, our fixed point becomes P star is equal to P max, as you can see here. Now, let me show you a little bit what this looks like for some fixed value of interaction. Now, if you consider we start at time 0, so at the start of the conference, what we have is an exponential growth to some equilibrium point. And we're supposing here that this interaction, which is fixed, is lower than the maximal interaction, which is why we don't reach P max. So we end up at some P star equals P collab, which is a probability that this pair of participants is going to form a collaboration by the end of the conference. Here, I'd like to take a little bit of a detour and talk about how we defined the interaction function throughout a conference. So again, we make a couple of different assumptions, and think about when you go to a conference here, especially maybe a setting that's a little bit more interactive, where you go into a room with a certain number of people. So we're considering that the interaction is symmetric. So the interaction between me and Nicholas is the same as the interaction between Nicholas and me. We also consider, and this is an assumption that we're planning to revisit at a later point, that participants spend an equal amount of time speaking in a workshop, which I think we've all experienced is not totally realistic. Usually some people who dominate the conversation and some people who speak less. And finally, we're defining interaction as proportional to one participant's time spent listening to the other participant. So first we define this I session. So as I mentioned, think of a session throughout a conference. Maybe you have 10 or 20 people in this workshop. And we're going to say that I session is proportional to the total time spent listening. So that's the total time T of this session minus the time that you spend talking. So T over N, if N is the number of people in the session. And you divide that by the number of people to listen to, which is the number of people in the room minus yourself. And that gives us T over N. So now we can define from this a sort of effective interaction intensity, which has a little bit of these strange units. It's to some extent a dimensionless quantity, but we're thinking of it as effective minutes over true minutes. So you can think of it as a weighted minutes according to how many people are in the room or how diluted the solution is, essentially. So I of T is going to be this I session of T over N divided by the time in the session, which is proportional to 1 over N. We're normalizing it so that when you're in a group of 2, when you're facing just one other person, that interaction is 1. So we end up with I of T equals 2 over N. And you can think also of these units as you can never really, you can't have an effective interaction that's greater than 1 minute. So the effective minutes per minute are sort of the, are the diluted minutes that you would spend speaking with someone, which would just be a true minute if you're only with one other person. And finally, we define this I total quantity. And that's just the integral from 0 to the end of the conference, which I call T conference here, of this I of TDT. So if you're attending a couple of different workshops with the same person, that essentially would sum that interaction at each of these sessions and multiply it by the time. So I total and I of T have different units. I total is in units of time. Okay, so maybe a little bit more of a concrete example of what this looks like. So on this top graph here, we have the effective interaction intensity in minutes per minute of a pair of participants at a conference that you might think of as a typical conference, from the time of the start of the conference at 0 hours to the end of the conference. So maybe the participants here are in a group of 4 people. You can see this is 0.5, so that would be 2 over 4. And then they interact to some level. Maybe they're together listening to a seminar with 50 people. And then maybe they go to a group with about 20 people. So for a little bit of a longer duration. So they have, again, this interaction. And then they go down and then they stop interacting throughout the rest of the conference. And you can see here what that translates to in terms of our linear model. So at the beginning of the conference, when they're not interacting, probability of collaborating is 0. And then it rises each time that they spend time interacting. And then finally, when the interaction ceases, you can see that this probability starts to decay at a rate which is different than the rate at which it strengthened when they were interacting. So there is a major limitation with this linear model. And this prompted us to develop what we're going to call the nonlinear memory model. And so the limitation with this is the fact that the probability is actually going to relax to p min after the interaction has ceased, which you could see in the slide I just showed. But what this implies is that people completely forget each other after having interacted, which is not totally true because, for example, Nicholas kindly invited me to speak today after seeing my talk a year ago. So maybe you meet someone at a conference, you interact with them some level, you remember them, you have a project that comes up that you think, oh, okay, this person would be great for me to collaborate with, and you send them an email, and that collaboration starts a year later. So you haven't totally forgotten them. So this prompted us developing our nonlinear memory model, which has an assumption that if people have interacted sufficiently strongly with one another, they will in fact remember one another after the duration of the conference. And so their probability of collaboration is going to remain at some higher non-zero level even after the interaction has ceased. Now, to develop this model, we're first going to reformulate our linear model as a potential. So we can describe the linear model as resulting from this quadratic potential, which we're calling V. So we can rewrite the equation as dp dt is equal to minus dv dp, where this minus sign is by convention so that the stable equilibrium is at the minimum. And you can see here what this would look like, the potential landscape of the linear model. And this is a case where the interaction and the probability are high, as you can see here. And now we can modify this potential flow to allow for more complicated potentials with multiple equilibria. And this is what we set out to do for our nonlinear memory model. Now we're going to make a couple of different assumptions here. Now, first, this is the case when the interaction is zero. So we'd like there to be two stable equilibria at p min, at p min and p mem, with a barrier that's going to be located in between them. And this is kind of a cartoon version of what we want this to look like at this point. So unstable equilibria in the middle. And we also make the assumption that when p is small and interaction is small, we'd like this process to be equivalent to our linear model that we showed earlier. Now, in the case where the interaction is maximal, you can see that the potential has changed shape. And so in that way, the conference acts as a catalyst by actually changing the shape of the potential. And so we make this assumption that when I is equal to I max, we'd like a stable equilibria at p is equal to p max. Well, here you can see a little bit what this looks like. As you increase the interaction, the potential deforms. So you start off in this case with no interaction, two stable equilibria, p min and p mem. Then at some critical value of interaction, you have a bifurcation that occurs, leaving only one stable equilibria, which is going to be at p star. And then when I is equal to I max, you're going to end up at your maximum probability. But here you have a little bit of an animation of the potential landscape with varying interaction. So here I'd like to show an example of the bifurcation diagram. There are a couple of different ways, or actually many ways, that we could have developed this nonlinear memory model, because there's a lot of different functions that can have this shape. So you can have quartic polynomial, you could have higher order polynomial, you could have whole bunch of different things that have this. But again, we're trying to apply this principle of parsimony and writing down the simplest possible model. So we're going to make some more simplifying assumptions. The first thing that we'd like to assume is that this barrier point, that's that unstable equilibrium between the minimum and the maximum, is located halfway between the minimum and the maximum. So you can see here, if the minimum is located when the interaction is 0 at 0.1 and the maximum is at 0.4, then the barrier is located at 0.25. Now, we also assume that there's this linear deflection of the fixed points, so that this P max is going to increase linearly with interaction intensity. And the same thing for this P minimum is going to increase linearly. And then on the other hand, the unstable equilibrium is going to decrease linearly. And they're going to meet at 1 here, which is for I over IC. So at this critical value of interaction IC, you can see that these two fixed points disappear, and we're only left with this other critical fixed point, which is here. The barrier disappears at this critical value of interaction. Okay, so as I mentioned, we went actually through a bunch of different iterations of this model. Our first choice was a quartic polynomial, which for various reasons just didn't work and didn't give us the behavior that we were looking for. So our final version was this piecewise function, which was composed of 4 parabola. And I'm going to go through just the different parameters that we have in this model here. So as I've mentioned earlier, we have Pmin and Pmem. You would have Pmax and Imax in the case where the interaction were greater. We also have these rates of strengthening, which we saw earlier for the linear model, and these are actually the curvature at the left and at the left here of each of the fixed points. So what we want is that the strengthening when you interact with someone towards this equilibria is going to be different from the rate of weakening. And this is actually why we decided to use this piecewise function as opposed to this quartic polynomial, because it allowed us to control the rates of approach to the fixed points. And then there's also this critical intensity, which is the value of intensity when the bifurcation occurs. Okay, so here I'd actually like to, show you a little bit how this model works. So let me actually paste this in the chat. If you're interested, you can go to this link, and we have an interactive version of our model. Oops. Are you guys seeing the interactive version right now? Or are you seeing the version? I think this is right. Okay.
Yeah, I think it's the interactive version that I'm able to access.
Great. Okay, so this shows how our model works, and you can change some of the inputs of the interaction, and you can also edit the values of the parameters here and see how the different models respond. So in this case, on the top, we have sort of a simple timeline between two people who attend a conference together. So they attend a first discussion together with, say, about 10 participants. And then they attend another small group discussion a little bit later. And then at the end of the conference, attend another 10 participant group. And on the lower graph, you have the probability of forming a collaboration. In orange is the linear model, and then in blue is a nonlinear catalysis model. And then on the left here, you can play around with the different rates of strengthening and weakening, which are equal at this point. So you can see here a major difference between this linear and nonlinear model. In the case of the linear model, you have an increase when they're in this in this medium group, let's call it. And then when they attend the smaller group, which is more intense, also an increase which decreases after, and then an increase again at the end. But in the case of the nonlinear model, they've interacted sufficiently during this small group. And so their probability actually has gone to that second memory value. And so it stays there and increases again from there at the end. And if you play around with the value of the critical interaction, that's going to change. You can also go to this tab here. I'll let this load for a minute. And you can see the value of the potential. And you can see how that changes as you increase. And at some points, I think we have the critical interaction here set to 0.2. So after 0.2, you should see that this first equilibrium has disappeared, and now we're only ending up with this second P star. And in the case of the linear model, you have only one equilibrium, whatever the value of the interaction is. Okay, so let me go back to my slides. All right, now data, which is perhaps one of the most exciting parts of this project for me. We partnered with this Research Corporation for Science Advancement, which is one of the oldest science philanthropy agencies in the country. And they've organized a series of conferences called the Scialog conferences, which stands for Science Dialogue. And the person who created these Scialog conferences, Richard Wiener, who's a physicist, actually had this amazing foresight already about 10 years now to start collecting kind of a crazy amount of data at a very good level of granularity about these conferences. So we have data analyzed about 12 conferences in 4 series over a period of 5 years, which you can see from here. And these conferences are on different scientific topics. They usually have an overarching theme, but they invite people related to that theme from different backgrounds. So it can be experimentalists and theorists, usually a little bit different from some of the conferences you might think about, like, again, APS or GMM, which are huge. These are very small, about 50 fellows who are invited per conference. It has a very interactive format, which is specifically aimed at generating new collaborations. And the fellows who are invited are these early career scientists. The sessions are facilitated by more senior people. So all in all, we analyzed over 13,000 pairs of potential collaborators. Now, at the end of these conferences, the participants have the opportunity to submit proposals together. Typically, 20 to 30 proposals are submitted, and 5 to 8 of them actually receive funding. So for the purpose of our work right now, what we're understanding is team formation or collaboration is actually the submission of a joint proposal at the end of the conference. In terms of data, we also have pre-conference survey data that was administered. So we know exactly how well every person knew every other person at the conference on a scale of 0 to 3. The fellows were also assigned using an algorithm to 3 to 4 medium and then 3 to 4 small discussion groups throughout the conference. And at the end of the conference, as I mentioned, they submit proposals together. These are self-assembled groups of typically 2 to 3 people, and sometimes goes to 4 people. To give you an idea of how many pairs ultimately collaborate, about 4% of pairs ultimately collaborate. So if you have 1,300 pairs per conference, which is typically what we have, that leads to about 50 collaborations. Okay, so before I get into the results of our model, I'd like to talk a little bit about some of the empirical results. Now, we first analyzed the first conference in each of the series because we wanted to omit the effect of people coming back from one conference to the next. So on this graph on the right, you have the mean total effective interaction for collaborators in blue. And this is using bootstrap estimates, which is what gives us our error bars on the left here. And then non-collaborators in red. So you can see that the total effective interaction of collaborators is much higher than the total effective interaction of non-collaborators. And this is true for conferences A, B, C, and D that we analyzed, and statistically significant, and especially true for the combination of all of the conferences. But with this, there comes a question, which is the question of causality. So one might think that maybe the people, it's not interaction that leads to collaboration, but it's people who are anyhow going to collaborate ended up interacting more. And that's what we wanted to test next. Okay, so here we tested, to test for this causal relationship, we used the algorithm that was used to assign the participants to the conference to generate 2,500 counterfactual scenarios. So you can think at the real conference, you have some timeline that every person is assigned to. And this algorithm actually generated a bunch of other alternatives which could have been selected instead of the one that was ultimately selected. So the hypothesis here would be that if it's not interaction that leads to collaboration, but it's some other factor, then you would see no difference between the mean total effective interaction time for those who collaborated compared to everybody else. It would just be some kind of random noise. So I'm going to go through this graph on the left a little carefully because I know it can be a little confusing. So here we're considering the actual collaborators, so the pairs who actually collaborated at the conference, and we're taking their mean total effective interaction time. So if there's 50 pairs who collaborated, we're looking at the mean of that, and that corresponds to 1 point. So I picked this 1 point here. So this is some alternate scenario. You consider the actual pairs of collaborators, and you can see that their mean total effective interaction is around 18. Okay. And this yellow line here, this represents the mean total effective interaction at the actual conference. Okay, now we're looking at these blue dots here, and these are also alternate scenarios. But they're the alternate scenarios where the participants were assigned to the exact same small group sessions. So I mentioned earlier, there's small groups, about 4 people, medium groups of about 10 people. All of these blue points at the top happen to be the 50 exact solutions for which the participants were in these same small group scenarios in the counterfactual reality. So in this case, it's a little bit higher than the actual conference. But you can see that on average, basically, the mean effective interaction is greater at the actual conference than at 99% of the other counterfactual scenarios. So it is, in fact, interaction which is leading to the collaboration. And so we went through another calculation, which I'm not going to go into detail here, but to test the difference between participants assigned to small groups and those who weren't. And we found that being assigned to one small group of 45 minutes actually increased your probability of collaborating 8 times. So think about it. You go to a conference that's maybe 3 or 4 days. If you end up in a group of 4 people for 45 minutes, you are 8 times more likely to collaborate with that person than any other scenario. So this is a question that's a little bit ongoing, but I thought it'd be interesting to show it to you here, because it's all fine and dandy to say, okay, we're showing that interacting in a conference leads to collaboration or team formation at the end of the conference, but does this actually impact science? So this graph here shows the percentage of pairs who published after the conference according to whether they were awarded funding. So were they a group who submitted a proposal and was successful? Were they a group who submitted a proposal but didn't receive funding? Or were they a group who just did not form a team, didn't submit a proposal? And you can see here that funding dramatically increases the likelihood of co-publishing by any 2 fellows. So if you group this in with the fact that we showed that interaction leads to collaboration, this means that the way you design your conference actually is going to have a great impact on publication, maybe a year or 2 or 3 out of that conference. Shifting a little bit back to our model, so considering this nonlinear memory model that we developed here, we wanted to validate the model by testing how well it predicted which pairs of participants collaborated. So first, we estimated the values of the parameters using maximum likelihood estimation. So again, this plot maybe is a little confusing. We're looking at the cumulative number of collaborations that are formed for increasing levels of interaction. So for example, an A, B, C, and D represent each of the conferences A, B, C, and D that we were analyzing. So if we take, for example, this point here in conference A, so this interaction, maybe 18, this shows the total number of collaborations that were formed for any interaction up to 18. And these triangles, these filled triangles represent the data, and the points with the error bars represent our model predictions. So you can see here that our model actually does very well at predicting the data. And in fact, out of 85 data points, I think there's only 1 that was not successfully predicted by our model, which I think is this one here. On the bottom here, E, this is just the residuals. So we also wanted to test our memory model compared to some other simpler null models. And we used the Akiki information criterion, which is defined as 2k, where k is the number of parameters in the model. So it penalizes for having more parameters to not have overfitting, for example, minus 2 times the log likelihood of that model. And we also computed the relative likelihood of that model compared to the next best one. So the models that we compared it to are two models based on randomness, one which was just assigning a totally random probability between 0 and 1 for any given pair to form a collaboration. A model that just had one random probability for all of the participants at the conference. Then we also tested three that were proportional to total effective interaction during the conference and or the prior knowledge before the conference, so how well you knew that person coming into the conference. We also compared it to the linear model, which was the first one that I described, and then what we called a threshold model. So basically, if you've interacted to some amount, then your probability is going to be something, and if you haven't interacted that amount, then your probability is going to be something else. And what we found is that our nonlinear memory model was preferred over all of these 7 other candidate models. And you can see this here in the values of the nonlinear model AIC compared to the next best model AIC. That value is a little bit less significant for conference B. If you're curious about why, I can talk about that later during questions. But this is really exciting because it means that our entirely empirical model, from the simplest possible assumptions about human behavior, led to predictions that beat any of the null models or any of these other correlational models. So somehow we've managed to capture something very interesting about how people form collaborations based on interaction. And we also found that conferences really lead to collaborations, and that's especially true for small groups. So I'm going to shift to a little bit of a different topic in a second. So if you have any questions, that might be a good place to pause for a minute and ask you guys if there's anything that I can clarify.
I think I have questions, but they're more involved, so I'll just wait till the end if that's okay.
Yeah, sure. Okay. So my next topic, which is related and is virtual conferences and pretty relevant for us today. So with the COVID-19 pandemic, we actually had this amazing natural experiment with the Research Corporation because they had like pretty much everything else in our lives to shift to a virtual format. So we've actually studied 7 virtual conferences and we actually recorded 18 breakout sessions at each of these conferences. That's around 160 hours of video of scientific conversation that we've recorded. Now, before I get into some of the results, I'd like to do a little poll here and see what your predictions are. Is interaction at virtual conferences less effective than interaction at in-person conferences at generating new collaborations? So you have the little emoji reaction feature in Zoom. So if you believe this is true, if you believe virtual conferences are less effective, give me a clap. And if you believe it's false, then give me a thumbs up. Okay, I'm seeing a couple claps, only claps. And then some people are not pronouncing themselves. If you have another prediction, please put it in the chat. I think about half of you thought that this was true, that virtual conferences were less effective at generating in-person collaborations. One person, Juan, believes it's false.
I just want to and see what happens.
Okay, so our prediction was pretty much the same as most of you, that interaction at virtual conferences was less effective than interaction at in-person conferences. I do want to put the caveat that everything I'm going to be saying after this is in a pretty particular context of the Scialog conferences, which are specifically aimed at generating new collaborations and are a very interactive format that you might not have in other virtual conferences. But what we found is that virtual conferences, in fact, can work. And not only can work, but that interaction at virtual conferences is actually more significant at predicting who ultimately collaborated than at in-person conferences. So here we have results. Again, we restricted ourselves to the first conferences in each of the series. So we looked at 5 conferences that were virtual in 2020 and 2021. This is kind of comparable to the graph you saw earlier where I showed you the difference between interaction for collaborators and non-collaborators. Also, this is about the same amount of data, so same amount of participants at each of the conferences. And we found that the significance of the interaction leading to collaboration is actually higher at these virtual conferences compared to in-person conferences. And not just that, but the size of the effect was actually greater. Now, what we attribute this to, and it's not necessarily a good thing or a bad thing, is that what this shows is that informal interaction is missing in virtual conferences. So in in-person conferences, you have all of those effects that we're not able to capture in the sessions where you have coffee breaks, you have meals, you have all of these informal interactions. Versus in virtual conferences, they tried including at the Scialog to do things like gather town, but those don't really seem to be leading to collaboration. So is this good or bad? Not necessarily one or the other, because of this fact that informal interaction is missing. So you can think that maybe some sort of participant-driven collaborations that would have been formed at an in-person conference are not being formed at a virtual conference. Sort of on the flip side, you can think of it as a more conference-driven team formation. So as a conference organizer, if your goal is to form teams, then you want to be doubly careful about how you're structuring your virtual conference, because that's really going to have a huge impact, even more so that at in-person conference, at determining who is going to form teams with who. Okay, so, and this is still work that's in progress to some extent. Now, let me just show you quickly this graph, which is comparable to what I showed you before, and goes along with our conclusion here, just showing that at the actual conference, there was only one out of all the counterfactual scenarios, all the 2,500 counterfactual scenarios, where there was greater interaction than at the actual conference. So this really means that what's driving the collaborations at the virtual conferences is the sessions that the people were assigned to. We've also started testing our model for the virtual conference, and we found similar results, that our model actually performed even better at predicting collaborations at the virtual conferences than the in-person conferences. Okay, so here I'm going to show you some, just a little taste of what's to come. There's many directions to go with this research, but this is kind of a fun one. So I mentioned that we have 160 hours of video, and Zoom actually doesn't provide the speaker info or the transcripts for breakout sessions like it does for main sessions. They might have updated the feature by now, but back when this started, it didn't. So we actually went and recorded all of these different breakout sessions. And so because of that, we had to find a way to actually get the data from these recordings. So we've developed this algorithm that takes the video, and here's my advisor, Danny Abrams, in this sample. We detect a little box that you can see in Zoom that has your name written in it. And from there, we detect the name of the person. And so what we end up with is a timestamp at which this specific person was speaking, and then the name of the person. And as you can see here, we've done this for a bunch of the sessions with pretty good accuracy in most cases, and still working on improving this. But again, just to give you a bit of a flavor of some of the questions that might come up with this, here I'm showing you the comparison of 3 discussion groups. So on the top, time is descending. So time 0 at the beginning of the conference is at the top for each of these sessions. And the columns represent different people who are speaking, and they're ordered by total amount of speaking time. So on the lower graphs, this is total speaking time. F stands for the facilitator of that session. And each of the numbers stand for the participants. G is just guests, funders, or things like that who attended the session. Now, just from these 3 examples, you can see some really interesting things. One thing, for example, is these patterns that are likely to emerge that are going to be consistent probably between many of the different sessions. So at the beginning here, you can see that it goes across each participant speaking for a small amount of time. And that sort of represents at the beginning of a session on Zoom where everybody goes around the room and says a little bit about themselves. Now in this first session, evidently the facilitator spoke a really disproportionate amount of time compared to all of the other participants in the session. In the second one, the facilitator was sort of more moderated. And in this third one, the conversation was really dominated by these three individuals. The facilitator spoke a little bit, but it seems that really there was a lot of back and forth between these three individuals. And so that leads us to a lot of interesting questions about the nature of scientific conversation and how moderators might, for example, distribute the talking time more evenly to make things more equitable. And with the data that we have, that repercussion on the actual formation of teams. So future work, I've mentioned some of our work with these scientific conversation. We also have a new postdoc who joined our group, Guy and Hai, who's working on this question of combining conference data with publication data. So what can we say about the inception of a collaboration from the people who attend the conference to several years later, and how does that affect their publication? Now, what we really hope to do, and we've already started to do a little bit with the Scialog conferences, is actually use this model and use our findings to optimize conference design. And I think that would be particularly useful going back to what I mentioned at the beginning for things like the Malta conferences, or just conferences in general that put a lot of resources and time into organizing these. How do you optimize that time that you have? We'd also be interested in testing our model and some of these findings with other types of conferences. So I think that's particularly true maybe for this question of virtual conferences. How does that compare for much larger conferences where you have a couple thousand attendees like the APS or the JMM, things like that. And also like the Malta conferences, regions of conflict where you might have other things that are impeding collaboration formation. But just to summarize, we found that conferences, even virtual conferences, are effectively influencing which teams are formed and are also, as a result, affecting the direction of science to some extent. So the way you organize your conference may have very well an impact on the directions that people are going to be taking in the science that they're going to be doing. Our model that was based on these very simple principles does surprisingly well at predicting the collaborations and outperformed all of those other models that we tested. And finally, we think that this could be applicable beyond science in other pairing scenarios. For example, in the corporate sector, team formation is also something that people are interested in, or in the educational sector. One that I find really fun myself is if dating apps were to give us their data, which they have a lot of, you could also test how interaction in this virtual dating setting would lead to pairings, in this case, the formation of romantic relationships. With that, I'd like to invite you to check out our preprint if you're interested in some more of the details of what we did here. I'd like to thank all of the people who have made this possible at Northwestern and at the Research Corporation for Science Advancement, our funders. If you have Twitter, you can follow me for more pictures of Merry and Pippin. I promise to post one of Pippin's double jointed tail. And also, I'd like to thank all of you for taking the time to listen to me today. And thanks you to Nicholas for inviting me. And I'd be happy to take any questions.
Oh, thank you. Any questions for our speaker? Tim, I guess.
Okay, so thinking back over my conference experiences, I've very rarely formed a collaboration based on a conference, but I much more often learned something that I then would put into a paper. And so I wondered if you've thought about perhaps tracking citations that come out of conferences, because that's one way I think that you might see that somebody learns something and maybe does something slightly different based on a conference.
No, actually, we hadn't thought of that, but I think that's a really interesting idea for sure. And I think it goes to my point about conferences sort of influencing to some extent the direction of science. So one way is collaborations that's maybe more impactful, but another more indirect way would definitely be citation. So yeah, thanks for the suggestion.
Rebecca?
Yeah, hi. That was really super interesting. I was curious about the role of time in the way that your model did predictions. Like, I thought it was really cool how you had that sort of long-term memory built in, but then it seemed like in your actual experimental setup, it was basically like the time when people would collaborate or not collaborate was sort of this fixed time at the end of the conference, but it wasn't entirely clear on like sort of when your predictions were being sampled from.
Yeah, that's a good point. I actually, yeah, I probably should have had that up, but the time at which we're sampling is this time at the end here. So there's a designated time for the people to form these teams and write their proposals together. And that's the time at which we're sampling. And I think your point brings up an interesting question of the different timescales in this problem. And I think there are a couple different timescales. I mean, so there is this timescale of a session, which might be 45 minutes, or typically how long the small sessions were, and then typically an hour and 15 for the larger group session. So there's a timescale of an hour, which is a session. There's a timescale of a couple of days, which is the conference, and then going into our future work with the publications, and you get into longer timescale of years. And so I think, yeah, that'll be really interesting to see how these different timescales play out on the collaboration.
Can I ask a follow-up?
Yeah.
Have you looked into like the difference? I'm not sure if this is really relevant, but like the difference between collaborators who shared a session like early on in the conference versus ones who shared a session later on?
Yeah, we did. We thought about that because the first conference we analyzed, conference A here, it kind of looked to us just different preliminary analysis that there seemed to be some effect. And that's a little bit common, something that we all think of, for example, that the first person you sit next to in college is going to become your best friend. But actually, when we looked over all of the different conferences, there was no significant effect of that. But what there was actually a significant effect was the effect of the first conference versus the repeated conference in the series. So that's one of the things that actually led us to just look at the data from the first conference in each of the series, because what we were seeing is that people pretty much form new teams more at the first conference. And then as it goes into the second and the third conference in the series, they start forming teams with people they know better and better. So the effect of just the sort of pure interaction of putting people in a room together seemed to decline to some extent as you go through the conference series. So going back to your timescale question, doesn't really seem to be true that on sort of the 3 or 4 day conference timescale, earlier is more effective at generating collaborations, but actually on the longer timescale, it seems that that is true.
Can I ask a question?
Oh yeah, sorry.
So I was wondering if you could, I mean, if you account for like round of the people who attend the conference, if maybe people who have similar backgrounds are have a higher probability of collaborating, or it doesn't have any effect?
Yeah, that's another good question. So I think there's a couple factors that come into play here. One is that for the Scialog conferences specifically, they're trying to get interdisciplinary collaborations formed, and they kind of reward that in their proposal process. So I don't know how representative this conference would be compared to other conferences, but I think that goes to a broader point, which is the effects of similarity, both in maybe scientific background, but also in terms of other factors for homophily. So maybe demographic factors or geographic location of your institution, or all of these other factors that could come into play in what form of collaboration. And I think these effects probably do come into play to some extent, maybe as a higher order. But I think what's actually sort of the power and the interesting thing about what we found is that despite all of these factors, just putting people in a room together, just exposing them to one another, that's sometimes called mirror exposure effect, Here it's a little bit more than mere exposure because they're interacting for a certain amount of time, but just putting people in a room together is enough to get them to generate collaborations, despite all of these other factors that might occur. But that's definitely something we have the data to test and something that I think would be interesting.
I had a question. So really quickly, so this is just looking at the time and the number or the sizes of the interactions. Have you looked at the way that these groups kind of intersect? So they're all just like sets of people, and maybe the interaction between these sets of interactions could like change things?
Yeah, I think that's another great point, and also something that is kind of in our future work plans. I think I made a really simple assumption at the beginning of this talk, and that's that we're considering a pair of participants. But obviously the effects are much more complicated because what we really should be looking at is the network of collaboration to some extent, especially because the teams that are formed are not just teams of 2 people, but they're teams of 3 people and 4 people. So there's absolutely network effects that come into play. But yeah, I put on our future work list here, where is it? These little Matryoshka Russian dolls. Because when we started this research, it really seemed that every time we found a question, there were like 50 other questions that emerged from it. So, but the network one is actually something that Guy, our new postdoc, is also planning to look at, especially in the context of the publications.
Cool, thank you. I think we are out of time, but let's thank our speaker one last time. Thanks so much, Emma.
Thank you so much for having me.
Cool.